All right, so we were talking about transformation stuff, right? We were just starting to. You played around with the little calculators I built for you, and you came up with some conclusions, right? So here's what we want to do. Our goal is, click these all the way close, please. For today, we want to be able to understand how the three parameters that we're going to use to describe an absolute value function, how we can use those to generate the graph of any function we want to, right? So one of the parameters was h. What does it do to a function if I add h to the x value? And you see that this is inside the function, right? So inside the function, f could be, in our case today, f of x is always going to be absolute value of x. That's our parent graph, right? But later on, it's going to be a quadratic function. F of x might end up being x squared. That might be our parent graph. Or later on in the year, it's going to be a square root function or a cube root function or a cubic function. It could be lots of things. But regardless of what the parent graph is, if I add h to x inside the function, what does that do? It's going to move it to the left. It's going to move it to the left 4 units.
Was that 4 units?
Yeah. Oh, I'm sorry, 8 units. I don't know why I was thinking.
really
Yeah.
Exactly.
I don't know why I was thinking. Where I came from. It's going to move it 8 units, isn't it? It's going to move it to the left 8 units. Now, what does it do here if we subtract h inside?
It moves it h.
It moves it h to the right. So we're going to go to the right h units. What happens if we add a k outside of the function? It's going to go up, because that's vertical, isn't it? So if we're adding something outside the function, that means it's going to go up k units. And if I subtract something outside the function, it's going to go down k units. Okay? All right, what happens? What about these? What about dilations? So if I'm going to multiply a function by a, if the absolute value of a is greater than 1, so like if it were positive 2 or negative 2 or something like that, what's it doing? Stretching. Okay, good. So if the absolute value of a is greater than 1, it's going to be a stretch. And it's going to be by a factor of a. Okay. What happens if a is less than 1? The absolute value is less than 1. So it could be negative 0.5 or positive 0.5. It's going to compress it. Okay. In this case, the factor is still just a, but when I multiply by a fraction less than 1, it makes something smaller, right? So the y values are getting smaller. Okay, and then the very last thing, what happens if the sign of a is negative? If we multiply a function by something that's negative, what does it do? Okay, it's going to reflect it vertically. Good. Okay, so if we wanted to do something then, let's summarize all this. So if we write some function, if p of x is our parent function, then the parameters a, h, and k completely control what we're going to do to that parent graph, right? As long as we're applying those parameters, it's going to have the same characteristics as the parent graph, but we can make it look like any version of that parent graph we want to, right? So those are what we call parameters in that. think of it like 3 dials, or an infinite number of functions that I could create from a parent graph by just dialing in those 3 values. If we wanted to summarize, what is h always going to be? H is always going to be
The opposite,
okay, and we could call that the horizontal
The X.
translation, right? So translation, think what translation means if you go back to geometry class. Translation means to slide something in the plane, right? So that's how far we're sliding the function. And the value of h tells us how far we're sliding in the positive direction, doesn't it? So for example, if I did something like if I had the function f of x equals negative 1/2 times x times p of x plus 4 plus 3. You tell me now, what are the values of a, h, and k there? So somebody tell me, what's the value of a?
Negative 1/2.
Negative 1/2. A equals negative 1/2. And what does that mean is going on?
This
Two things.
slope becomes negative and stretches.
Okay, but don't think of it in terms of a slope. The slope, it applies in some cases, like an absolute value function, you could argue it applies a little bit. But we don't want to think about it in terms of a slope. We want to think about it in terms of what we're going to call a dilation factor, right? All of the distances, the vertical distances, the height of the function are going to be multiplied by negative 1/2. What's that going to do? It's going to compress it, and what's the negative doing? Reflect it. Okay, so we're going to reflect vertically and compress. Those are the 2 things that are being done by that A. Reflect vertically and compress. What's the value of h? Now be careful with this one.
Negative.
Okay, it's negative 4. You see that? Because h is the value that's being subtracted from x, right? So if I have x plus 4, that's the same thing as x minus what? Negative 4, right? So we see here, and that's one that's a little bit tricky. It takes a second to kind of calibrate your thinking on that. So h is equal to negative 4, which means we're going to move to the right by negative 4. Well, what's it mean to move to the right by negative 4? Going left by 4. Okay, everybody see that? H is the amount we're going right, so that means we're going left 4. Okay, and then finally, what about k?
3.
K is equal to 3, and so what is that telling us? K is so H was the horizontal translation. That's the vertical translation, right? How much we're going up. So we're going up by 3. Well, what if K is negative? To go up by a negative means you're going down, right? So K is 3, up 3. Okay, so now that's a good question. So that's the question that always comes up next if you're thinking about this. Do you go, I think, say it again, Kate.
It's just like, right, when the first one was negative 1/2, so we reflected it, and then h was 4.
No, the H is, right, the H is inside, so the A is what's outside. So this part right here, it's the part that's being multiplied by the whole thing that says we're reflecting. Okay, H is what's being subtracted from X inside the function. So that's doing a different job. Subtracting something from X is telling us how far we're sliding it to the right. Okay, multiplying the function by something out front is telling us how much are we stretching or compressing this thing. Okay? All right, now by order of operations here, I want you to tell me which of these things do we have to, what's the order in which I should apply these transformations? And I want you to really pay attention to this because this is important. By order of operations, what would we have to do first?
H.
Okay, technically we do H first, wouldn't we? Because we're going to do work inside the parentheses first, so we're inside the function. Everybody agree? Okay, so first we would slide this thing left 4, then what would we do? then I have to multiply, right? So the next thing would be we're going to apply the reflection and the vertical compression, and then the very last thing we do is what? We're gonna slide it up by 3, okay? I wanna show you why that's important. Let's look at an example where we're gonna graph one of these things. Like what if we do something like this guy, okay? We wanna do a graph here of this function, okay? So we wanna, I need a grid. Let me get a grid.
Very welcome.
Okay, so real quick, what's vertex form for an absolute value function? Okay, would it be what? A times the absolute value of
X minus H
x minus h
plus K.
plus k. Good, so there's vertex form. So what are the values of the parameters? What's a?
Oh wait, negative
Negative 2.
Negative 6.
And then the vertex is at hk, right? So what are the coordinates of hk?
Negative 6, negative 3.
Okay, so let's try this one then. Where's the vertex located? Negative 6, negative 3, so it's right there, correct?
Yep.
Okay. Now, we're going to compare this function to the shape of the parent graph, right? The parent graph, remember, is the one that's going to go over 1 and up 1. Oops. It's going to go over 1 and up 1, over 2 and up 2, etc. Right? So there's the parent graph. We want to draw the red transformed graph, though. So if A is negative 2, tell me the roadmap from the vertex to where I'm going to have a point on my graph. So normally out from the vertex, I would go over 1 and up 1. What am I going to do here?
Down 2 over 1.
Okay, over 1 and down 2, right?
Yes.
So normally we would go over 1 and up 1, right?
Yeah.
But the job of the dilation factor is to tell us what we're going to multiply the normal vertical amount by, right? So we're multiplying positive 1 by negative 2, so going down by 2. Okay? So that's going to give us a point right here. And really, for an absolute value function, how many points do you need? I mean, really, like 1, right? Because that's, as long as I can draw straight, that's giving me the shape. I mean, it's just a straight line. It's a ray, actually, isn't it? And then once I get that 1 point, it's really a 2 for the price of 1 deal, isn't it? Because I know I'm going to have another one that's reflected to the other side, right? What would I call that vertical line right there that splits the absolute value function?
The line of reflection.
Okay, line of reflection, or even better, a line of symmetry, yeah, right? We'll reflect over that line of symmetry, and that's our answer, isn't it?
Wait, doesn't it, reflect?
Okay, so
Yeah.
you're right, it reflects, but think why it's reflecting. If you think about the fact that this A is a negative 2, what's going to happen if I'm multiplying a positive y value by a negative number? It's going to go down instead of up, so that causes the reflection, doesn't it?
Wait, so there, okay.
You see what I'm saying?
Yeah.
So once again, rather than thinking about this as a bunch of 4 discrete steps, you can really break this into just 2 processes if you use the vertex form. Step Step one is we're gonna locate the vertex. Step two is we're gonna pick a convenient y value and multiply it by a, right? To get the dilated y value. Instead of going over 1 and up 1, we're going over 1 and up 1 times negative 2, which is down 2. Okay, one more. What about that one? Let's work through this one together. We can probably do this pretty quickly here. We'll probably run out of time. But what's our vertex going to be?
Negative 1, 2.
Negative 1, 2. Everybody agree?
Yeah.
Okay. So negative 1, positive 2 is our vertex. Now normally we're going to go over 1, up 1, over 2, up 2, over 3, up 3, over 4, up 4, etc., right? On both sides. Okay, now what's A?
A is negative 44/3.
Okay, negative 4/3. So the dilation factor is negative 4/3. So I want you to think really strategically about this. Which point on my parent graph should I use to create my dilated point? Like if I go, I'll give you an example. If I go over 1 and up 1, now I'm going to go over 1 and up negative 4/3. So go down, negative 4/3 is not a very convenient place to make a point.
No, not necessarily. You can multiply it by some number to get an even number or something. I don't know.
So I'm always going to be multiplying the vertical height of my function from the vertex by the dilation factor. What's a convenient number to multiply by 4/3? 3, right? So why don't we pick the point that goes over 3 and up 3. So if I multiply the vertical height from the vertex, 3, by negative 4/3, what's 3 times negative 4/3? Once again, 3 times negative 4/3. Negative 4, aha. Okay, so I'm going to go down now. I'm going down by an amount 3 times negative 4/3 equals negative 4, right? So I'm going down by 4, and that gives me a pretty convenient place. So down 4 and over 3.
So if it's negative,
why three?
obviously,
Say it again.
because 4/3.
Three is not gone.
Right? You see why we want to use that point? Because it's convenient.
So it's almost like it's just negative.
Okay, so we know that I'm going to multiply. I want to pick a normal parent graph vertical distance that's going to be compatible with this number that I can multiply by 4/3. Well, that would be 3, wouldn't it? So ask yourself, I want to multiply the vertical distance 3 by negative 4/3 to get negative 4, right? But to go up by 3 on an absolute value function, how far do I have to move to the right? To go up by 3, I have to move right by 3, right? So instead of going over 3 and up 3, we're going to go over 3 and we're going to multiply that 3 times negative 4/3 to give me a negative 4. So that's telling me that that's dilating that point is all it's doing. Right?
So it's almost like a reciprocal.
Well, in this case, I mean, yeah, that's why we picked the 3, because 3 times negative 4/3 is negative 4. We don't end up getting some mixed number there. We get an integer amount, so it's a convenient point for us to graph. You see my point?
So is it a slope, just rise over run?
So A, okay, right, so A is a slope for an absolute value function. I want to caution you against thinking about it that way, though, because just peer ahead a little bit in the class. We're going to do the same thing very shortly to a parabola, where our parent graph is x squared. But is there such a thing as a slope on a parabola? It's not a line. See what I'm saying? And so that's why you always want to kind of think about it as a stretch factor or a dilation factor. You're right, because the original piece of the absolute value graph that we're dilating is just a straight line with a slope of 1. You're always going to be multiplying that by the dilation factor to give you a different slope, right? But you see why I'm saying that, though? Like, if we were going to be talking about a parabola, I'll give you an example. See if you can tell me what to do here.
Wait,
I
so
bet
just
you can't.
negative, kind of flip it, That's how we get like a 3/4.
So what if we started off with this? What if I started off with, okay, we're jumping way ahead for just a second. So if you don't, if this is, we haven't even talked about this, so don't panic if this doesn't make total sense. What if I've got a parabola written in vertex form? It's gonna look like this. It's gonna look like one half x minus 1 squared minus 3. Where do you think the vertex is of this parabola?
1, 3.
1, negative 3 is exactly it. Okay, because this also, what we're gonna see here in about 3 days is that we can write a parabola in the form a times the quantity x minus h squared plus k, and the h and k means the same thing. It means the coordinates of the vertex, and a means the dilation factor, right? So what would this look like? Where's my vertex going to be for this one? It's going to be at 1, negative 3, correct?
Yes.
Everybody agree? So at 1, negative 3, now what am I doing? I'm compressing my parabola by a factor of 1/2. So it's going to end up being squished, right? Okay. So the height of the parabola from the vertex is only going to be 1/2 as big as it used to be before I compressed it. So let's start by graphing a quick version of our parent graph. For a parabola, a normal parabola, when I go 1 to the right, how much up do I go? 1. When I go 2 to the right, I go up by 4, right? So I'm going to be up to about there. Okay, and I go back, and I go back by 1, and I go, so it looks kind of like that. It's not a very good parabola, but you get the idea. There's my parent graph, right, the parent shape. Now when I multiply this by 1/2, what's going to be the most convenient point to squish down so it's only half as tall?
Perfect squares.
Wouldn't it be the one, yeah, wouldn't it be the one that I went over by 2 and up by 4? Because 4 times 1/2 is 2, right? So we're going to go over 2 and only up 2. And what's that going to do? It's going to give me a shorter, wider parabola. It's going to look like that, right? Well, why didn't we want to use this point? Because going over 1 and up 1, if I multiply 1 by 1/2, I don't get a nice convenient point. Okay. We'll keep doing it.